Time to travel back in time. Number 10. The Minoan eruption of Santorini. Sometime around 1600 BCE, a volcanic island in the Aegean Sea did not simply erupt. It annihilated itself. The Minoan eruption of Thera, the ancient name for what we now call Santorini, released energy equivalent to thousands of nuclear weapons in a matter of hours. And it did so without leaving a single written eyewitness account, without a survivor's testimony, and without any warning that history was about to be buried under meters of ash and pumice. What remained was a crescent-shaped scar in the sea, a caldera roughly 83 square kilometers in area, and a silence where a thriving civilization had been. Before the eruption, Thera was a cosmopolitan hub of the ancient Mediterranean world. The Minoans, based primarily on Crete, roughly 110 kilometers to the south, had built one of the most sophisticated Bronze Age civilizations on Earth. They had indoor plumbing, multi-story palaces, elaborate frescoes, and a maritime trade network that stretched across the eastern Mediterranean. The settlement on Thera itself, preserved today beneath volcanic deposits and excavated at the site of Akrotiri, was a prosperous and densely populated town. Its streets, storage jars, and painted walls frozen in time by the very catastrophe that ended it. What makes the Minoan eruption particularly haunting is not its violence, but its silence. Archaeologists excavating Akrotiri have found no bodies, no skeletons, no human remains. The residents appear to have fled before the final cataclysm, warned perhaps by precursor earthquakes in the days or weeks before the main event. They took their valuables and they left, but they did not come back. Where exactly those thousands of people went, and what became of them after the eruption reshaped the entire eastern Mediterranean region, remains unknown. The eruption ejected an estimated 60 cubic kilometers of material into the atmosphere, sending a column of ash and gas 35 to 39 kilometers into the stratosphere, high enough to alter weather patterns across the ancient world. Tephra deposits from the event have been identified in Egyptian sediments, Turkish tree rings, and Greenland ice cores, where a sharp acid layer marks the moment the volcano fired its contents into the sky. The scientific debate surrounding this eruption is itself remarkable. Two separate lines of evidence point to two different dates, and they disagree by over a century. Radiocarbon dating and ice core evidence consistently suggest the eruption occurred around 1628 BCE, while traditional archaeological dating of pottery styles and Egyptian historical records places it closer to 1500 BCE. The gap matters enormously, because if the earlier date is correct, the eruption may have caused the famines and darkness mentioned in Egyptian records, and may have contributed to the instability that helped end the Bronze Age. If the later date is correct, those connections dissolve. After decades of research, no consensus has been reached. The island gave us an extraordinary catastrophe and then refused to tell us exactly when it happened. In 1939, Greek archaeologist Spyridon Marinatos proposed that the Minoan eruption was the real event behind Plato's legend of Atlantis, a sophisticated island civilization that sank beneath the sea in a single day and night. Most scholars treat this as an intriguing hypothesis, rather than a confirmed identification. But there is something genuinely unsettling in the parallel. An advanced civilization, an island destroyed by geological violence, a story passed down through centuries until it became myth. The people of Thera fled their homes and vanished from the historical record. What they carried with them, and what they remembered of the world before the sky turned dark, we will never know. Number 9. The Campanian Ignimbrite eruption and the end of the Neanderthals. 39,000 years ago, a volcanic system beneath what is now the western suburbs of Naples, Italy, erupted with a force that had no precedent in European geological history. The Campi Flegrei supervolcanic system, known in Italian as the Phlegraean Fields, produced what geologists call the Campanian Ignimbrite, a vast sheet of superheated gas, ash, and rock fragments that incinerated everything it touched across hundreds of thousands of square kilometers. It was the largest volcanic eruption in Europe in the last 200,000 years, and it may have delivered the killing blow to a species that had survived for 400,000 years. The Campanian Ignimbrite eruption ejected approximately 300 cubic kilometers of material into the atmosphere, enough to bury an area the size of France under several meters of volcanic debris. The resulting ash layer, known to geologists as the Y5 tephra, has been identified across an extraordinary geographic range, from the Atlantic coast of Europe to the plains of the Middle East, from the North African coastline to the lake sediments of Central Asia. The eruption produced a volcanic winter of uncertain duration, suppressing plant growth and collapsing food chains across the northern hemisphere during an already fragile glacial period. What makes this eruption genuinely chilling is its timing. Neanderthals had survived ice ages, climate shifts, volcanic events, and roughly 400,000 years of a harsh and unforgiving world. Modern humans, Homo sapiens, had recently arrived in Europe from Africa. The Campanian Ignimbrite eruption occurred at almost precisely the moment when Neanderthal archaeological sites begin to disappear from the European record. A 2022 study published in Nature Communications, led by researchers including Eileen Schmucker and Paolo Marsocchi, found a direct correlation between the eruption's ash deposits and a sharp decline in Neanderthal population signatures across dozens of European sites. The timing is not coincidental. It is almost impossible to argue that it is. What scientists cannot yet confirm is the precise mechanism. Did the eruption directly kill Neanderthal populations across a wide area? Did it collapse their food sources, forcing already stressed groups into competition with modern humans for dwindling resources? Or did it simply accelerate a decline that was already underway, tipping a weakened species past the point of recovery? Researchers favoring the volcanic explanation note that Neanderthal sites thin and disappear in a pattern that radiates outward from the Campanian eruption zone. Those more cautious point out that modern humans were expanding simultaneously, and that disentangling two overlapping pressures is extraordinarily difficult with 39,000-year-old evidence. Today, 3 million people live in the greater Naples metropolitan area, directly above the same volcanic system that produced the Campanian Ignimbrite. Campiflegrei is not dormant, it is restless. The ground across the Phlegraean fields has been rising measurably for decades, a process called bradyseism, driven by magmatic fluids moving beneath the surface. The Italian government has contingency plans for the evacuation of the region. Scientists monitor the system continuously. Whether the next eruption of Campiflegrei will be a minor event or something approaching the scale of 39,000 years ago is a question volcanologists take seriously, and one that has no comfortable answer. Number 8. The hidden caldera of Cerro Galan. In the high Andes of northwestern Argentina, at an elevation of approximately 4,500 meters above sea level, there is a geological feature so large that the people living within it had no idea what it was. The Cerro Galan caldera, located in Catamarca province, measures roughly 35 kilometers by 20 kilometers, making it one of the largest calderas on the surface of the Earth. Its true scale was not appreciated by geologists until aerial and satellite surveys in the latter half of the 20th century revealed its complete outline. It had been hiding in plain sight, too enormous to see from the ground. The eruption that created Cerro Galan occurred approximately 2.08 million years ago, during the Pleistocene epoch, at a moment when early members of the genus Homo were taking their first tentative steps across the African landscape. The volcano produced the Cerro Galan Ignimbrite, a deposit of welded volcanic rock estimated at approximately 1,000 cubic kilometers of material, among the largest eruption deposits identified in South America. Ignimbrite sheets from this event covered thousands of square kilometers of the Puna Plateau, a high-altitude tableland that today forms one of the most remote and sparsely inhabited regions of South America. What makes Cerro Galan particularly puzzling to volcanologists is how little studied it remains compared to supervolcanic systems of similar or even smaller scale in other parts of the world. Yellowstone attracts continuous monitoring and global scientific attention. Campi Flegrei is watched by one of the most sophisticated volcanic observatories in Europe. Cerro Galan, despite producing a caldera larger than many of its more famous counterparts, receives a fraction of that attention. The remoteness of its location, the altitude, and the political and logistical challenges of working in the high Andes have all contributed to a significant gap in our understanding of one of Earth's most violent geological features. What is known is striking enough. The system produced multiple eruption phases across millions of years, with the main caldera-forming event at 2.08 million years ago being the most studied. The caldera floor contains evidence of ongoing geothermal activity, with fumaroles and hot springs indicating that the magmatic system beneath has not fully cooled. Researchers including Robert S.J. Sparks, who conducted foundational work on the caldera in the 1980s, established the basic framework for understanding its structure, but subsequent detailed studies have been sporadic. Volume estimates for the main eruption range from roughly 650 to 1,050 cubic kilometers, a wide margin that reflects not controversy, but simply insufficient data. The deeper implication of Cerro Galan is not about what we know, but about what we do not. If a caldera 35 kilometers across went unrecognized as a volcanic feature until geologists deliberately looked for it from the air, the question is not rhetorical. How many similar structures exist in the world's remote mountain ranges, in the deep ocean basins, in the poorly mapped interiors of continents, still waiting for the right vantage point to reveal what they are? Cerro Galan is not merely a large volcano. It is a reminder that the geological inventory of this planet is still incomplete. Number 7. Long Valley and the Bishop Tuff. 760,000 years ago, a catastrophic eruption in what is now Eastern California produced a single volcanic deposit that geologists can still identify in soil profiles from Nebraska to the Mexican border. The eruption that created Long Valley Caldera, located in Mono County near the present-day Sierra Nevada, released approximately 600 cubic kilometers of magma in what may have been a matter of days, collapsing the ground above into a caldera 32 kilometers long and 17 kilometers wide. The deposit it left behind, a thick sheet of welded volcanic glass and ash named the Bishop Tuff after the nearby town of Bishop, California, became one of the most extensively studied ignimbrite deposits in the world, a geological Rosetta Stone for understanding how supervolcanic systems work. The Bishop Tuff is, in its way, extraordinary. Geologists Christopher Hildreth and Colin Wilson dedicated careers to unraveling its secrets, publishing foundational research that revealed the tuff was not produced in a single uniform pulse, but in a rapid sequence of eruption phases, each drawing magma from slightly different depths within the underlying reservoir. The chemistry of the deposit changes subtly from bottom to top, recording in stone the precise order in which different layers of the magma chamber were emptied. It is a frozen snapshot of a geological catastrophe, detailed enough to reconstruct the eruption almost minute by minute, if you know how to read the rock. What makes Long Valley unsettling today is not its history, but its present. In May of 1980, 4 magnitude 6.0 or greater earthquakes struck the Long Valley region in rapid succession, prompting the United States Geological Survey to issue a formal notice of potential volcanic hazard for the area, the first such notice ever issued for a caldera system in the continental United States. The earthquakes reflected movement of magmatic fluids beneath the caldera, not simply tectonic adjustment. Since then, the USGS Long Valley Observatory has maintained continuous monitoring of the system, tracking ground deformation, earthquake activity, and gas emissions. The caldera floor has measurably risen and fallen over the decades. The system is not sleeping. Mammoth Mountain, the ski resort that sits on the southwestern rim of the caldera and draws hundreds of thousands of visitors each winter, has been releasing carbon dioxide gas from its volcanic foundations since the early 1990s. The CO2 has killed trees across roughly 100 acres of the mountain's slopes, the dead trunks standing as pale monuments to the gas seeping invisibly from below. The USGS documents this phenomenon openly and monitors it as a volcanic hazard indicator. The resort operates normally. The mountain continues to exhale. The Long Valley system is classified by the USGS as a high-threat volcano in the National Volcanic Threat Assessment, a designation based on both its eruptive potential and its proximity to populated areas and critical infrastructure. The ski lifts at Mammoth Mountain run directly above a magma system that last expressed itself by blanketing half a continent in ash. The mountain gives no indication it has forgotten how. Number 6. Toba and the human bottleneck. 74,000 years ago, a supervolcano on the island of Sumatra in present-day Indonesia produced what is now recognized as the largest volcanic eruption in the last 2.5 million years of Earth history. The Toba eruption precisely dated through argon isotope analysis to approximately 74,000 years before present, with an uncertainty of roughly 2,000 years, ejected an estimated 2,800 cubic kilometers of material into the atmosphere, a volume nearly 5 times larger than the largest known eruption of Yellowstone, and almost entirely incomprehensible in human terms. The caldera it left behind is 100 kilometers long, 30 kilometers wide, and up to 505 meters deep, today filled with water to form the largest volcanic lake on Earth. Before the eruption, anatomically modern humans had been present in Africa for at least 100,000 years, and some populations had already begun dispersing toward the Middle East and South Asia. The world they inhabited was complex, populated by multiple hominin species, including Neanderthals in Europe, Denisovans in Asia, and various archaic human populations across Africa. Life was difficult, but viable. Then Toba erupted, and the ash layer it produced has been found in sediment cores from the South China Sea to the Arabian Peninsula to Eastern Africa, a visible line in the geological record, marking the moment the sky turned dark. In 1998, anthropologist Stanley Ambrose of the University of Illinois published a hypothesis in the Journal of Human Evolution that has been debated ever since. Ambrose proposed that the Toba eruption caused a volcanic winter lasting 6 to 10 years, followed by a prolonged cold period lasting up to 1,000 years, and that this climatic catastrophe nearly drove humanity to extinction, reducing the global human population to perhaps fewer than 10,000 individuals. The evidence Ambrose pointed to was genetic. Modern humans display strikingly low genetic diversity compared to other great apes, a pattern consistent with a severe population bottleneck occurring sometime in the past 100,000 years. The timing aligned uncomfortably well with Toba. The hypothesis remains contested and should be presented as such. Archaeologist Michael Petraglia and colleagues published findings in Science in 2007 suggesting that stone tool cultures in southern India survived the Toba eruption with apparent continuity, casting doubt on the idea that the event was universally catastrophic. More recent genetic studies have questioned whether the human bottleneck corresponds precisely to the Toba date, or whether it reflects an earlier or differently timed event. What is not contested is that the genetic bottleneck is real. Modern humans are, genetically speaking, a remarkably uniform species, and something in our evolutionary past produced a period of extreme demographic stress. Whether Toba caused that moment or simply coincided with it remains one of the most consequential open questions in the science of human origins. What is certain is this: every person alive today is descended from a population that survived the aftermath of the largest volcanic eruption in 2.5 million years. The ash from Toba is still findable in the soil of 3 continents. The lake it left behind sits placidly in Sumatra, ringed by tropical forest, visited by tourists who photograph its blue waters without necessarily knowing that they are standing at the edge of the event that may have nearly erased everyone who came before them. Number 5. The Emeishan traps and the forgotten extinction. 259 million years ago, in what is now the Sichuan and Yunnan provinces of southwestern China, a volcanic system began to tear open the surface of the Earth. The Emeishan Large Igneous Province, as geologists call it, was not a single eruption, but a sustained continental flood basalt event that buried hundreds of thousands of square kilometers under layer upon layer of lava, releasing vast quantities of carbon dioxide and sulfur dioxide into the atmosphere over a period geologists estimate in hundreds of thousands of years. It produced one of the largest lava accumulations in Earth history, and it coincided precisely with a mass extinction event that eliminated the majority of tropical marine life on the planet. You have probably never heard of it. The Emeishan eruptions occurred during the Campanian Age, the final stage of the Middle Permian period, approximately 259 to 260 million years ago. The lava flows and associated volcanic deposits cover an estimated 300,000 square kilometers of modern China, with original coverage before erosion likely considerably larger. The volcanic activity released enormous quantities of greenhouse gases, triggering rapid warming of tropical ocean waters and a collapse of oxygen levels in shallow marine environments. Reef ecosystems, among the most biologically diverse environments on Earth, were devastated. Studies including work by Paul Wignall and colleagues published in Science examined mercury anomalies in geological sections from the Campanian boundary, providing direct chemical evidence linking the Emeishan eruptions to the biological collapse recorded in the rocks. The extinction associated with the Emeishan traps, sometimes called the Campanian or End Guadalupian extinction, eliminated roughly 80% of tropical marine species and fundamentally restructured ocean ecosystems. These are not small numbers. An 80% loss of marine species represents a catastrophe of extraordinary scale, the kind of event that would dominate our scientific attention and popular imagination if it stood alone in the geological record. The reason it does not is that it was followed, 7 million years later, by something even worse. 7 million years after the Emeishan traps began erupting, a second and far larger flood basalt event, the Siberian traps, initiated in what is now northern Russia. The Permian Triassic extinction that followed eliminated 96% of all marine species, the largest mass extinction in the history of complex animal life. Researchers studying the relationship between these two events have proposed a disturbing possibility that the Emeishan eruptions weakened global ecosystems so severely, destabilized ocean chemistry so thoroughly, that the biosphere was significantly more vulnerable when the Siberian traps arrived 7 million years later. The Campanian extinction was not merely a catastrophe in its own right. It may have been a preconditioning event, leaving a damaged world less capable of absorbing the next blow. The Emeishan traps are rarely mentioned outside specialist geological literature. They eliminated most of tropical marine life on Earth and barely register in public consciousness against the catastrophe that followed. It is a measure of how extraordinarily violent this interval of Earth's history was that a near-total collapse of ocean ecosystems across the planet counts, in geological terms, as a footnote. Number 4. The Deccan traps and the death of the dinosaurs. 66 million years ago, as a 10-kilometer asteroid was completing its final approach toward the Yucatan Peninsula of what is now Mexico, another catastrophe was already underway on the opposite side of the planet. The Deccan traps, a massive flood basalt province in what is now west-central India, had been erupting for at least 250,000 years before the asteroid struck. Lava flows up to 2 kilometers thick had already accumulated across an area of roughly 500,000 square kilometers. The planet was already stressed, its climate already destabilized by volcanic gases, its ocean chemistry already shifting, before the impact that most people associate with the end of the dinosaurs added its own catastrophic signature to the geological record. The Deccan traps ultimately produced somewhere between 1.5 and 2 million cubic kilometers of basaltic lava, covering what geologists estimate was originally as much as 1.5 million square kilometers of the Indian subcontinent before erosion and plate tectonics rearranged the landscape. The eruptions released enormous quantities of carbon dioxide and sulfur dioxide over a period spanning hundreds of thousands of years, causing global temperature fluctuations estimated between 2 and 8 degrees Celsius across the 500,000-year interval surrounding the Cretaceous-Paleogene boundary. In 2015, a team led by geochronologist Paul Wren and colleagues at the University of California, Berkeley, published findings in Science establishing that eruption rates in the Deccan system increased significantly within approximately 50,000 years of the Chicxulub asteroid impact, suggesting that the shock waves from the impact may have intensified the already active volcanic system on the other side of the globe. The relationship between the Deccan traps and the end Cretaceous extinction is one of paleontology's most genuinely contested debates. The asteroid impact at Chicxulub is the dominant explanation in mainstream science, and with good reason. The Chicxulub impactor released energy equivalent to billions of nuclear weapons in a fraction of a second, triggering wildfires, a global impact winter, and an acid rain event of extraordinary severity. The evidence for its role in the extinction is overwhelming, but Princeton University paleontologist Gerda Keller, among others, has argued for decades that the Deccan traps alone were sufficient to cause a major extinction event, and that the impact, arriving on an already stressed biosphere, was the final blow rather than the primary cause. Keller's position is a minority view among researchers, but it is not a fringe one. It is based on detailed stratigraphic work spanning multiple continents. What the combined evidence suggests is deeply unsettling. The non-avian dinosaurs, along with roughly 75% of all species on Earth, did not die from a single cause arriving on a single day. They died from a convergence of catastrophes, a planet that had been gradually destabilized by years of volcanic gases and climate disruption, struck by an impactor that then accelerated and amplified the volcanic activity already underway. The world did not simply end. It was dismantled, systematically, and from multiple directions simultaneously. The Deccan traps today form some of the most distinctive landscape in India. Their layered basalt cliffs visible in road cuts and river valleys across Maharashtra and neighboring states. The rock is dark, dense, and almost featureless, carrying no obvious sign of what it once was. The physical remains of a multi-100,000-year volcanic crisis that helped empty a world. How often does Earth arrange itself so that two extinction-level forces arrive in the same geological instant, each amplifying the other, each ensuring that nothing survives to recover before the next wave arrives? Number 3. Yellowstone and the Sleeping Giant. Beneath Yellowstone National Park, where tourists gather every day to watch geysers erupt on schedule and photograph bison crossing thermal flats, there is a magmatic system of extraordinary size and violence. The Yellowstone hotspot has produced 3 caldera-forming super eruptions in the last 2.1 million years, each one large enough to reshape the climate of the northern hemisphere and bury significant portions of North America under ash. The youngest of these eruptions occurred approximately 640,000 years ago. The oldest, the Huckleberry Ridge eruption, occurred 2.1 million years ago and released an estimated 2,500 cubic kilometers of material, depositing recognizable ash layers across 31 U.S. states, reaching into Mexico and Canada. Yellowstone is not a scenic curiosity. It is one of the most consequential volcanic systems on the surface of the Earth. The Yellowstone hotspot has been creating a trail of calderas across the Snake River Plain for approximately 16 million years, as the North American tectonic plate moves southwestward over a stationary mantle plume. The calderas left behind form a chain of progressively older volcanic scars stretching across southern Idaho toward Oregon, each one the remnant of a previous super eruption. Yellowstone itself is simply the current position of the hotspot, the most recent point in a long sequence of buried worlds. The 3 major caldera-forming eruptions at the current Yellowstone location, at 2.1 million, 1.3 million, and 640,000 years ago, represent only the most dramatic expressions of a system that has been erupting in smaller ways far more frequently throughout its history. What makes Yellowstone genuinely disturbing is not its past, but its present behavior. The USGS Yellowstone Volcano Observatory monitors the system continuously using a dense network of seismometers, GPS sensors, and ground deformation instruments. The caldera floor rises and falls by measurable amounts annually, driven by the movement of hydrothermal fluids and magmatic gases through the crust. Earthquake swarms occur regularly beneath the park, sometimes numbering in the hundreds of small events over periods of days or weeks. In 2017, a swarm of more than 2,400 earthquakes struck over a 3-month period, the largest swarm recorded at Yellowstone since monitoring began. The USGS noted at the time that the activity was within normal parameters for the system. Normal, in this context, is a relative term. The USGS classifies Yellowstone as a high-threat volcano in its National Volcanic Threat Assessment, the most serious designation in its rating system. The agency is careful to note that Yellowstone is not overdue for an eruption, explicitly rejecting the popular framing that the 640,000-year interval since the last super eruption implies the next one is imminent. Geological systems do not operate on calendars. But the magma reservoir beneath Yellowstone is real, well-documented, and active, extending approximately 90 kilometers in length at depths between 5 and 14 kilometers. A second, deeper reservoir has also been identified. The system has the fuel. Whether it will find the trigger is not a question science can yet answer with confidence. If a Huckleberry Ridge scale eruption occurred at Yellowstone today, the immediate effects within several hundred kilometers would be unsurvivable. Ash fall thick enough to collapse roofs and contaminate water supplies would affect much of the continental United States within days. Agricultural disruption across North America would be severe and prolonged. The injection of sulfur dioxide into the stratosphere would likely cause a volcanic winter affecting global food production for years. These are not speculative worst-case scenarios. They are the modeled consequences of an eruption that this system has already produced, in this location, within the span of human evolutionary history. Every year, millions of people drive into Yellowstone and stand above the largest volcanic system in North America, watching water boil out of the ground, and call it beautiful. They are not wrong. They are also standing on the roof of something that has ended worlds before and is still very much alive. Number 2. La Garita and the eruption that broke the scale. 27.8 million years ago, in what is now the San Juan Mountains of southern Colorado, a volcano erupted with a violence that has no parallel in the last 66 million years of Earth history. The La Garita caldera event, precisely dated through radiometric analysis to 27.8 million years ago during the Oligocene epoch, produced the Fish Canyon Tuff, a deposit of volcanic material now recognized as the largest single eruption product ever identified in the geological record of the Cenozoic era. The volume of the Fish Canyon Tuff is estimated at approximately 5,000 cubic kilometers, a figure so large it effectively renders the standard frameworks for comparing volcanic eruptions inadequate. To understand what 5,000 cubic kilometers of ejected material means, consider the reference points from this list. The Toba supereruption, the event that may have nearly driven humanity to extinction 74,000 years ago, produced approximately 2,800 cubic kilometers. Yellowstone's largest known eruption produced approximately 2,500 cubic kilometers. La Garita produced 5,000. The Volcanic Explosivity Index, the standard scientific scale for measuring eruption magnitude, formally maxes out at a value of 8. A category that encompasses the largest eruptions recorded in the past few million years. Some researchers examining the Fish Canyon Tuff have suggested that the scale itself is simply insufficient to describe what happened at La Garita 27.8 million years ago. The eruption does not fit the framework. The framework needs to be expanded to accommodate it. The La Garita caldera left behind a depression approximately 75 kilometers long and 35 kilometers wide, one of the largest calderas identified anywhere on Earth. Like Cerro Galan in Argentina, It was not immediately recognized as a volcanic feature by the geologists who first mapped the region, because a caldera of this size does not look like a volcano from the ground. It looks like a landscape. It was only through systematic geological mapping in the 20th century, tracing the extent of the fish canyon Tuff and working backward to its source, that the full scale of the La Garita system became apparent. The research of volcanologist Barry Lippmann and colleagues was instrumental in establishing the caldera's geometry and eruptive history. What the Fish Canyon Tuff eruption did to the global climate 27.8 million years ago is not fully understood, and this is itself a significant scientific statement. The climatic consequences of Toba have been modeled extensively because they occurred within the time frame of human history and have potential relevance to our own evolution. The Fish Canyon eruption occurred 27.8 million years ago in a world populated by early primates and archaic mammals, in a configuration of continents and ocean currents substantially different from today's. Modeling its climatic impact is considerably more challenging. What can be said is that an eruption of this magnitude almost certainly injected sufficient aerosols and ash into the atmosphere to cause significant global cooling and disruption, the full extent of which has never been systematically calculated. La Garita is the largest known eruption of the last 66 million years. The word known carries considerable weight. If a caldera 75 kilometers across went unrecognized as a volcanic feature until geologists deliberately searched for it, the question of what else remains unrecognized in the geological record is not paranoia. It is methodology. The Fish Canyon. Tuff stands as the largest measured expression of terrestrial volcanic violence in the age of mammals, a benchmark so extreme that it resets the sense of scale for everything that follows. And yet, even at 5,000 cubic kilometers, it is not the most destructive eruption in Earth's recent history. That distinction belongs to something older, larger, and incomprehensibly more complete in its destruction. Number 1. The Siberian Traps and the Great Dying. 251.9 million years ago, at the boundary between the Permian and Triassic periods, a volcanic event began in what is now northern Siberia that was not an eruption in any ordinary sense of the word. The Siberian Traps, large igneous province, was a continental-scale catastrophe, a sustained outpouring of lava, ash, and volcanic gas that lasted for approximately 1 to 2 million years, covered roughly 7 million square kilometers of the Earth's surface in basaltic rock, and released quantities of greenhouse gases so staggering that a 2020 study published in Science Advances calculated the total at approximately 100,000 billion tons of CO2 equivalent. It is the largest volcanic event in the last 500 million years of Earth history. It coincides exactly with the Permian-Triassic mass extinction, the most devastating extinction event in the history of complex animal life on Earth. The coincidence is not a coincidence. Before the Siberian Traps began erupting, the Earth was fully inhabited. The Permian world was rich with life, particularly in the oceans, where complex reef ecosystems housed an extraordinary diversity of species that had been evolving for hundreds of millions of years. Trilobites still existed in reduced numbers, a living connection to the Cambrian. Synapsids, the ancestors of modern mammals, had diversified into dozens of forms and dominated many terrestrial ecosystems. The seas were warm and biologically productive. Life was not merely surviving. It was flourishing in the intricate, interconnected way that only hundreds of millions of years of evolution can produce. The eruptions changed everything, and they did so through multiple simultaneous mechanisms that compounded and reinforced each other over thousands of years. The initial volcanic activity injected sulfur dioxide into the atmosphere, causing short-term cooling and acid rain of extraordinary severity. As the eruptions continued, carbon dioxide accumulated in the atmosphere and oceans, driving rapid warming estimated at 5 to 10 degrees Celsius above baseline. The warming oceans lost their oxygen, a process called anoxia, creating vast dead zones in the deep sea that expanded relentlessly toward the surface. The contact between rising lava and the thick coal deposits of Siberia produced additional greenhouse gases, including methane and carbon monoxide, accelerating the warming beyond what the volcanic CO2 alone would have achieved. Hydrogen sulfide, a toxic gas produced by anaerobic bacteria in the oxygen-depleted oceans, began rising into the atmosphere in concentrations lethal to terrestrial life. The kill mechanisms did not arrive one at a time. They arrived together, overlapping, each one making the others more effective. The result was the Great Dying. Approximately 96% of all marine species disappeared from the fossil record at the Permian-Triassic boundary. Approximately 70% of terrestrial vertebrate species were eliminated. The loss of taxonomic diversity was so complete that paleontologists studying the boundary can identify it in rock outcrops worldwide by the sudden disappearance of familiar fossil forms and their replacement millions of years later by a drastically simplified fauna. Coral reefs, one of the most biologically complex ecosystems on Earth, did not recover for approximately 10 million years. Some groups never recovered at all. The trilobites, which had survived every previous extinction event in 270 million years of evolutionary history, did not survive this one. Life on Earth came closer to complete elimination at the Permian-Triassic boundary than at any other moment in the last 500 million years. And the cause was not an asteroid, not a gamma-ray burst, not a collision with another planet. It was a volcano. A volcano that erupted for 1 million years. What the Siberian traps did to this planet should be understood not as a historical curiosity, but as a demonstration of what Earth's internal geology is capable of producing. The same processes that drive plate tectonics, the same mantle plumes and rifting events that have shaped the continents and oceans across billions of years, are capable, under the right conditions, of generating sustained volcanic outpourings that sterilize entire biospheres. The Emeishan traps did it on a smaller scale 7 million years before the Permian ended. The Deccan traps contributed to a second extinction 186 million years later. The Siberian traps did it most completely, most devastatingly, most finely, reducing the complex, diverse, deeply interconnected web of Permian life to a thin thread of survivors clinging to a poisoned, overheated, oxygen-depleted world. It took 10 million years for life to recover anything approaching its previous complexity. 10 million years. The entire history of the genus Homo, from our earliest ancestors to the present moment, fits inside that recovery interval with room to spare. The Siberian traps did not merely bury a world. They unmade one. And the world that grew back in its place was so different that the event serves as the primary boundary between two of the great chapters of animal life on Earth. Whatever came before, it belonged to one story. Whatever survived belonged to another. If you want to see more videos like this, click the video on screen now and make sure to subscribe.